This is S603 from Xinjiang High School, and I'm going to report problem number 3, spin on the rod. And here's the problem statement. The washer on the vertical steel rod may start spinning instead of simply sliding down. Study the motion of the washer and investigate what determines the terminal velocity. And here we'll mainly focus on how different parameters of the washer influence the motion and how to find the phenomenon of terminal velocity and angular velocity. And this is our outline. We will start with an observation video and then move on to our theory, then our experimentation, and finally our conclusion. And here are our observation videos from the side view and the top view. And as you can see, the ring is rotating on the rod, and we think that is a combination of the spinning motion and the precession. And here is the preliminary observation of the theta 2 times graph. And you can see that when it's beginning to drop, the theta of t has an angular acceleration at first. And when it's spinning stably, it will come to a terminal angular velocity. And if we capture the part that is stable and fit it to a linear growth, you can see that the R-squared value is really close to 1. So we can say that the gradient of the slide is our terminal angular velocity. And here's our theory. First is precession. Precession is a phenomenon in which an object not only spins itself, but the axis that the object spins around will spin around another axis. And except for the precession and the spinning, nutation will also occur in this case. Nutation is a phenomenon when the angular velocity of the washer is not big enough. The axis of rotation of the washer will swing up and down on the vertical line and become an irregular motion. And here are some definitions. Omega s is the spinning angular velocity, and omega p is the precession angular velocity. A is the counterpoint of the ring and the central axis, and RC is the distance between the central mass, between the mass center and the z-axis. And also R1 is the inside diameter, and the theta is the inclination of the ring. And here, and also the rings, at first the ring's force is not balanced, so it will become, the gravity will have a moment on it. And to prevent from the falling, there were two conditions. One is the frictional force between the washer and the rod, and another one is the maximum theta due to the structural limits of the rod and the ring. And here we define the P1 and P2 as the contact point of the ring and the rod. And here, the normal force here is equals to the centrifugal force that when the washer is spinning, and it can be written like the m times r times omega squared. And we can get the frictional torque by multiply it with a coefficient of friction and the distance of the axis and the force. And also we can get the gravitational torque like this. So if the two torques are the same, it will become a rolling motion, but not sliding off. But the washer will not slide off. And here we will use the spherical coordinate to describe the motion. And also we will use a system called Euler's angle. And this phi is the angle that is spins in the original spinning motion. And the theta is the inclination angle of the washer, and it is also the z-axis, and the axis 3 include the angle. And the phi and the psi is the precessional velocity's angle. And after that, we can get the E1's, E2, and E3's vector units by using all these three angles and some of other axes. And after that, we can get our omega, which is the acceleration of the ring, by using of this, and also we can get the moment of inertia by using some theorem. And we can see that I1 is equals to I2 because the ring is symmetrical. And after that, we can calculate the kinetic energy that the washer has. And also we can calculate the omega 1 squared plus the omega 2 squared. So after that, we can also find the position of the center mass. And after doing some differential to the equation, we can get the velocity of the center mass and also the acceleration of the center. And here we will use the Lagrange mechanism to obtain some of the EOMs, which is the equation of motion of this phenomenon. And to use the Lagrange mechanism, we will assume that there's an energy conservation during this motion, and also it is only a periodic motion, and the rod we're using is the smooth rod. So L here is defined as the kinetic energy minus the potential energy. And the potential energy here is only the gravitational potential energy, and the kinetic energy is the summation of the rotational energy and the falling energy, and which can be written like this because we have got it calculated for it in the first page. And after that, we can write out our L and insert into the Euler's equation to obtain the theta, phi, and psi. And after that, we can also draw a graph about these three variables. And after that, we can take a look at these two graphs. And as you can see, all of them comes to a stable condition, just like our experiment shows, because it will come to a terminal angular velocity. And we can get our angular velocity by using the previous Lagrange mechanism, and also the falling velocity and the equation of motion. And here comes our experimentation. And here we will use a 7.7 millimeters rod and different washers as our ring, and also a vacuum tweezer to release our washer. And as you can see, we lock the rod on the equipment and insert the vacuum tweezer on it, and we can let the washer release natural and to prevent our effect of our hands and observe the phenomenon. And this is our expectations from our theory. And here this comes to our first parameter, is the inside diameter. And here in our theory, we found that bigger inside diameters will lead to an increase, will lead to a decrease on the angular velocity. But in our experiment, it grows up a little and drops substantially. And we can get the falling velocity of this from a side view. And in our theory, bigger inside diameters will let the falling velocities increase. And from the experiment, the end of the velocity becomes smaller, and we will discuss the data which doesn't match the theory in our discussion part. And here's the second parameter, which is the outside diameter. And as you can see from our theory, we can know that bigger outside diameter will lead to the angular velocities decrease. And in our experiment, the trend goes up a little and decline next. And also from the side view, we can observe the falling velocity. In our theory, bigger outside diameter will let the falling velocities decrease. And in our experiment, there's one data which is different from the trend. And in our discussion, we're talking about what is the difference between the ideal situation and the real condition. And as you can see, it is not totally an energy conservation, which is ignored in our previous assumption. And also, specific inside diameter and outside diameter ratio will influence the energy lost. And here's the comparison of the smooth rod and the spiral rod. First, spiral rod will let the friction force become bigger, and it will lead to a stable condition of the washer. But it will also let the give the washer an initial angular momentum. But also, the spiral rod may cause some energy loss because it has a bigger friction. And also, the spiral rod will cause a little nutation, like what I just mentioned. And here's our conclusion. For dropping, smaller friction force, bigger mass, bigger inside diameter, and smaller outside diameter, and a smaller incline angle can make the falling velocity slow. And also, the angular velocity, which is the bigger inside diameter, bigger outside diameter, bigger thickness, and a smaller incline angle can make the angular velocity slope. And these are references, and these are my report. Thanks for your attention.
Okay, so please answer my question, yes or no. First question is, does mass affect the terminal velocity of the washer? Does mass affect the terminal velocity of the washer?
We didn't check the variable.
Okay, next question is, did you consider a number of the contact points between the rod and the washer?
No.
No, okay. The next question is, do you think inertia of the washer is constant or changing throughout the motion?
What do you mean by
inertia. Moment of inertia, do you think it's constant number or it will withdraw?
It's a
Constant, okay. Do you think the center of the mass of the system will be fixed throughout or no? Center of the mass of the system fixed. Do you agree that the period of the translation and period of the revolution and period of precision of one revolution is the same or no?
No.
No. Do you consider different phase of the washer's motion throughout?
No.
Do you believe initial force affect terminal velocity or no?
It will not affect the terminal velocity.
Do you consider thickness of the washer or gap between the threaded rods? Or did you consider threaded rod at all?
Just the thickness of it just influences the moment of inertia.
Okay, so did you consider threaded rod or only the smooth rods?
We did it on a spiral rod, but in our theory we use a smooth rod.
Okay, thank you. Do you think rotational direction will matter of the terminal velocity? If you rotate counterclockwise or clockwise, will it be affect your overall terminal velocity?
And if we use the spiral rod, it will become just no matter.
So you please say yes or no.
It will depends on what.
Okay, depends on do you agree that camera viewpoint cause the false displacement? Because for perspective, the camera gives you the tear or the tiltedness. So do you agree that your video is falsely show the displacement? When you check?
Little.
Little, okay. I'm Hyunwoo Chun from the All-Nighter, and today I will propose number 3 ring on the rods. So I thought the main focus of the problem is how does the washer transition from the simple sliding motion of to the spinning motion, and what and how the parameter affect the translation and rotational terminal velocity of the washer. For my perspective, I'll structure the problem statement, solving the problem statement by first talk about the 3 phases of motion, because we need to also consider translation. The reporter did not mention about it with the rotation and precession. And we also need to talk about the contact points, because different number of the contact points give different number of the force that we need to analyze in the free body diagram. Then I'll move on to the theory, talk about the force and torque analysis, and derive those analysis to find the terminal velocity. And I'll use 3D inertia tensor instead of just using the fixed inertia tensor, because the washer is moving and it has a different inertia throughout the motion of the phenomenon. And then also we will consider the center of the mass is not fixed, but it's rather moving based on the rotation of the washer. And we will also talk about the drag force. And then I'll talk about expectation of discussion of how omega t or dt precision are related, and also talk about the transition case. So reporter did a pretty good job for the clear video demonstration, and theory used Lagrangian and the Euler's equation, which is really strong. And then he also showed the experimental setup clearly. However, the cons is that for the experiment, rod and top view is unstable, and there's more error. And then also there's no fit with theory lines or no error. So we cannot tell whether he had only 1 point or multiple points. Also, there are lack of reasoning for the conclusion, and the few data points and the parameter are missing. So for the upcoming discussion, I want to talk about theories about the number of the contact points, 3D inertia consideration, or the center of the mass consideration, and I also want to talk about how the gap in between the rod and the washer will impact to the overall motion. And as we talk about this in 2-minute discussion, I want to bring up this topic, why the reported thing, those are the same. And then I want to also talk about the mass impact onto the terminal velocity. Then I want to talk about the experimental setup, for example, like how the holding is not strong, so it can cause the vibration of the rods while the washer is moving down. And also it's possible that the camera point cause the false angular velocity where the film are shifted or the sheared. Also, since the reporter considered about the threaded rod, the gap between the threaded rod is larger than the thickness of the washer, the theory will not work. I'll explain it later. In the parameter, I want to talk about the direction of the spinning and use of force and omega with the threshold. And then I also want to talk about different dimensions of the washer, rod, and type of the rods. And then I also want to talk about the contribution of the threaded portions. And after that, I want to also move on by adding some analytical data points, like they did not use error, so the number of the trials is inefficient. And also we want to talk about the test not enough variables trials, and then should test variable determine the terminal velocity. So I want to move on to the discussion for now.
Okay, so sorry about the misunderstanding. So can you explain what is the translation of?
Translation, yes. Because you said that the motion is only of the precession and the rotational.
Yes.
Precession meaning wobbling, yes. And rotation meaning rotating. But as you can see, the terminal velocity is also translating moving down to the y direction, z direction. So that's meaning the translation. Yeah. So can you go back to slide 9? So you put slide 9 on simulation for the ring. So this is not a ring, it's the cylinder. So how?
This is just an explanation of the mutation.
Okay. So you're not based on anything for this simulation?
Yes, no.
Okay. Can you move on to slide 14? How can you guarantee that the washer axes are always fixed? Based on the wobbling, it could be possible that axes are different. So I thought that we need to use the parallel axis theorem to consider those parts to calculate the inertia. So what do you think about that first?
So from here you can see that all the axis is from the center of mass. So and it is also a symmetrical structure of the ring. So I think we can still define the inertia.
Okay. And then you said that inertia is the way you find inertia. Can you go back to slide 14? The way you find inertia is you're plugging a number. But however, I think that when you consider the inertia of the washer, let's say this is washer, I think you need to consider in XX direction, y direction and also a z direction. Because washer is changing, so you cannot just assume that it's going to be just constant number. So I think you need to use the inertia tensor where it gives you in different direction. So what do you think? What is your reasoning for just calling inertia just a constant? All these 3D motion.
So, and I think this is a this is a wrong part we left down. But so, what do you think about just calculating the inertia on the x, y, and z axis? So because we think that it is symmetrical, so whatever spins, this looks like this when
for example, if you make symmetrical, this is the axis, or do you think this is symmetrical?
Just like if it rotates here, we can still budget on this side.
Okay, so you think it's revoluting, so it's going to be
Yes.
Okay, thank you. So you talk about that you didn't consider the number of the contact points, but you analyze with the normal force. So the number of the contact points will matter for the calculating the force. So how did you not considering the contact points, but then use the force diagram to analyze it?
Just like we combine all together.
Combine it together.
Yes.
Then how many contact points do you think the rod and washer are making?
When it's in a stable condition, it's 2.
2? Okay, thank you. And then you said that the center of the mass system will be fixed. But
Because,
for example,
the height is not fixed.
sorry,
The height is not fixed.
height, the
The,
center of the mass system,
the z-axis is not fixed.
z-axis is not the same. But do you think it's also possible to moving around in x and x direction? Like for example, let's say this is rod, yeah. So wouldn't it be also oscillating this one because washer is going back and forth? So
we should do that.
okay, sounds good. So you said that the mass will not affect the terminal velocity in the 2-question-minute discussion. So can you explain why the mass does not affect the terminal velocity?
Yes,
of the washer?
because I think that the mass, you can just, in our theory, you can just, because the mass is constant with the force, but the force is, the final terminal velocity is associated with the acceleration, and it would not really.
Yeah, I sort of agree with that, but adding to your points, you talk about when you reach the terminal points, there's only friction force happening. So although the mass is increasing and weights make the weight increasing, the friction force is also increasing, so it will equal out, cancel out together to make the terminal velocity constant. That's what I think about it.
But the gravitational force is also increasing. It's also become bigger.
Could you explain why gravitational force is increasing? Because mass is constant.
When the mass is become just adjust the mass, then it become bigger. So.
But gravitational force is F equal mg. Then m is constant and g is constant. So how does the gravitational force
change the m and the mg?
Oh, we were talking about the same washer. We did the same washer. Yeah.
Yes.
So in the same washer,
yes.
when you in each independent washer, as you increase the mass by using different washer, do you think the terminal velocity will be changed or no?
It will become different.
Different? But as I mentioned, I think it's going to be same because weight and the friction force will equally cancel out each other. Let's go on to the next point. So you said that the period of the translation, like one revolution, and translation of the rotational and translation of precession are the same. So do you have any calculation or graph that show you that those are the same? Okay, then, okay, I think you mentioned about the rolling without friction.
Just like a road, you can think it is a rolling motion.
Right. Yeah. But then the rolling motion is based on your assumption that your motion is only based on the rotational and precession. But when you think about the translation, when you look at the translation viewpoint, it's rather sliding, so it's not rolling in the translation in the z direction portion. So how would you do you think you need to modify that the friction is not anymore rolling without friction, or no sliding, or no?
No sliding.
No sliding. You still believe there's no sliding?
Yes.
Okay. My next point is I brought about the phase. So if you think about the terminal velocity and then here's gonna be the frame because you use the video to film it. I think there's a point where it's unstable at the beginning, but then it increasing velocity, it's increasing, but decelerating, and then it reaches the terminal velocity. And then I thought that you didn't. Yeah, did you consider this part or no?
So this is the transition.
Yeah, so at the beginning this is unstable, but it starts to get to the stable two contact points, and it will decelerate. Yes. So when you film the video, which phase did you measure from here? Like which portion did you start to measure?
Just like when the release of the, we'll just capture the stable part of it because it is easier to determine how the sum of the parameters associated with the terminal velocity.
Okay, that makes sense. Can you go back to the how the setup parts or the video? Can you explain how did you? Yeah, so this is top view, right?
Yes.
But then I believe that when you look at the top view, or when the washer is going down, let's say the top view original size is like this. But when you go forward, the length is going to be shorter. So as I mentioned in the question, the viewpoint for the camera will make the shear or the tiltedness. So how would you account this part when you find the
Because
displacement?
it will become smaller when it's going down, so we just count the angle that moves.
Right.
So the angle won't be affected by the distance.
Okay,
of the,
that makes sense. However, when you look at the front view, so if you, let's say you're zooming here, then your focus is correct here, but the washer will be overestimated. Then it seems like it's moving fast, and then it became the realistic one, and it became the fast. Because angle is tilted from the camera.
we decided to film it far from the rod.
Oh, so you feel from far from
From the rock.
here. Or I was thinking that maybe when you analyze with the vector to find the washer, you can change the basis vector that makes it perpendicular, not like shear or tilted. So that's my suggestion for next time. Yeah. And then I also want to talk about rod vibration. Can you go back to the this one's good. So as you can see, the rod is not clamped in the top. So as you can you do you have more bottom like clamp parts? Do you have the front view of the setup? That's fine. Let's look at this. So it's not clamped. So
I think this is because we're just using our hands to capture because it is not for experimental. And you can see that it is.
okay. But my point is, since the washer is rotating,
Yes.
it makes the rod also vibrating,
Yes.
and it will cause the external normal force that. So that's the point I want to mention, that if you didn't clamp it well so it's vibrating, your theory will not work. But your theory is only based on the washer and the rod interaction,
But we're
not considering the
just
vibration.
focused on the terminal velocity of the washer. So we don't think that the vibration at first will affect the terminal velocity of any.
But as you can know, each material has the resonance part. So when it reaches a certain frequency, it will amplify it, and it could make the error not negligible.
So it will not cause much great vibration because it's like this, and we also the equipment we use is. That's why we found it. It is stick on the wall, and the platform is stable. The rod is in
So basically we talked about the translation, rotation, and precision, where the reporter did not really talk about the translation. So there's some misassumption about ignoring the translation motion with the 3D inertia motion. And then we also talk about define and accounting change on the fixed axis. That we need to find, if you want to use the inertia equation, we also need to use the parallel axis theorem, or you can also use the 3D tensor of the inertia. You can also, we also talk about the number of the contact points, the changing center of the mass position, and mass effect on the terminal velocity, where I think it won't change any terminal velocity effects. And then we also talked about rolling without friction. And this one is part that unclear because translation seems like it's slipping rather than rolling without slipping. We also talked about different phase measurement as we can either on the board. And for the experiments, we talked about setup suggestion, the top view, and then for the basis vector changing to make it more correctly. And also we suggest that those angle tiltedness. Thank you.
Okay, thank you for the recorder. And upon the first question I would like to ask is that if the mass of the ring increase and the terminal velocity will increase or decrease?
Stay the same.
And how much?
The same.
Okay, and the second question is about, have you considered about the slide and the rotation together, or is it separate things? The slide of the ring and the rotation.
Could you repeat for me?
Slide, just like slide down and the
Yeah.
rotation together.
But it's following the path like spirally, so
Yeah,
I'm not sure about
that's
your
how
question.
We didn't consider about the study.
Okay, and another question is about angular velocity and linear velocity is in this phenomenon. And which one did you guys think is more important?
Both of them are important because I think they're related. Where the time in which the terminal angular velocity equal to the terminal
Okay, I see.
translation.
I think the same with you.
Okay, and if the rod will shake like vibrating, will the terminal velocity be easier to get to or not? Not that easy to get to the terminal.
It's based on the case. It could be decreasing normal force, or it could be increasing normal force, and it will affect the proportion to the friction force.
I don't think the vibration will affect that.
So you think it won't affect the terminal velocity?
Just if there's no much.
Okay, I got it. The next question is predict if you use a different material like of the rod, and how will it affect the terminal velocity, like the bigger friction of the rod?
For example, if you use threaded rod instead of smooth rod, it will make the overall. It will think like you can have the thicker smooth rod by using the threaded rod. That's what I think.
Yes, I got it.
It's just about the friction force.
So the friction force got bigger, and how is the terminal velocity?
It will become smaller.
Okay, and there's two kinds of friction, and the kinetic friction and static friction. So which one is more important in this kind of phenomenon?
As I told you, translation is sliding, and then rotation and precision is kinetic. That's
So
what
you think both is important?
But the other way, but yeah, both is important.
Okay, I got it.
So we didn't consider the sliding, so we think it's only the static friction.
So you just consider about static friction, right?
Yes.
Yes. And another question is using a rod which has a bigger radius, the rod, and how will affect the phenomenon?
I think bigger radius is less important than the gap in between the inner radius and the rod radius. The difference, those are more important than the washer's radius.
Okay, I got it. And how about
So just like we just mentioned in our conclusion.
okay, and can you say it again?
So sorry for not familiar with it. Just
Okay.
just
Just say it. How would the rod, the radius of the rod change, and how would the terminal velocity change?
So we time
Okay.
out.
opponent. I'm the reviewer of this question. And here's the problem statement, and we main focus on the terminal velocity, the angular velocity, and the slide down of the washer. And here's the summary of the reporter, and he just explained the phenomenon and the terminal velocity, and also in the theory, he including the notation and the process and the torque analyzed, and he also did some circular coordinate and some energy conservation and the maximum angle that the washer. And the experiment he did have different kinds of parameters and different kinds of rod. The pros of him is explain the force diagram of a ring, and the cons that of the reporter is no phenomenon explanation and does not quantify the initial speed and lack of the considering of the contact point that the opponent has said, and the center of the mass isn't fixed. Okay, and here's the pros and cons of the opponent. The opponent has the clear and concise short questions that he asked and point out the contact point and some pretty interesting questions, and point out the full experiment method like the camera. And the cons is that it did not clarify the terms and did not give the evidence of their theoretical claim. Okay, and here's the first question that the reporter and the opponent discussion about. And here's the initial of the report in page 14. The report says because the axis is to the line, so it can be seen by its solution. And the opponent says we should use the initial tensor. So the reviewer just agreed with the opponent's idea. Okay, and the next question is about the contact point. The reporter just says the normal force can be combined in a force, so that's considered about the contact points. And the opponent says there's two contact points, and this will affect the normal force. And the reviewer thinks we agree with the opponent, but they will have to show the evidence of the two contact points and how the two contact points is going on. Okay, and the next question is about, the discussion is about the mass of the terminal velocity, and I also think this is an important question and I asked in a short question. And the reporter just said the terminal velocity will change with the mass of the ring, and the opponent says that the terminal velocity will be the same even the mass is bigger. So the reviewer thinks because of the gravity and the frictional force will cancel the formula, so the terminal velocity won't change. So in this question, we agree with the opponent's idea. So here's the point mixed. And the first point mixed is about did not consider the sliding. And as the reporter says, we have to consider about the sliding of the rod and the rotation together because this is a system. Another missed point is about no considering about the parameters of the rod that I have told in the short question, and I think different kinds of material can be used, like the different metals, and it will have different kinds of different friction by different material. And the third one is about how the friction and the initial condition affect the velocity, and will it becomes faster or will it become slower, and also will the terminal velocity stay the same. So this is the end of my presentation. Thank you for listening.
Learned a lot more about this phenomenon, and we really appreciate the opponent and reviewer for the great discussion. And there's one point I want to explain, that we use the vacuum tweezer and the platform to make sure every release is the same and will not affected by our hands. And for the theory part, we should use different rods in the theoretical assumptions and the experiment, which is about the smooth rod and the spiral rod. And also the transformation, not only about the precession and the rotation. And we should also take the direct motion into our consideration. And we haven't invested more in the different mass of the ring. And the terminal velocity should be the same when from the opponent's view and the reviewer's view. And the angle will not be affected when it's falling down, and we didn't consider about the sliding. And also for the experimentation part, we should do more investigate in the clockwise or the counterclockwise rotation, and we didn't consider the mass of the ring. And from the front view, we shouldn't just film it in a certain precision. And also the material causes different friction, and this is another parameter we can try to do. And these are my report. Thanks for your kind attention.
Okay, now it's time for a question from juries.
So I think all of you agree that the mass will not change the terminal velocity.
Yeah.
Which one of you really did the experiment? You have experimental data to support you.
Also, because I'm opponent, can I still talk about the experiment I did?
Yeah, sure. You have experimental data that support that the mass does not affect the terminal velocity.
Oh yeah. So we test different ways of the washer, and then we use a tracker to follow the center of the mass, center of the washer throughout, and then both of them reach to the same terminal velocity value.
Okay. How about you?
I guess because if we turn the mass, so the radius of the ring may follow the mass, so increase. So this.
You need to do the experiment just.
No, because this is two parameters in one experiment, so we can't do this kind of experiment.
How does the vibration of the rod affect the terminal velocity? Please answer me in the order of the reviewer, the reporter, and the opponent.
Sorry about it, I would like to see them.
Should the vibration
because,
increase or decrease the terminal?
I think because the terminal velocity would decrease because it will increase its normal force, so the terminal velocity will decrease.
I don't think that the vibration will influence the terminal velocity because it's just like when we release it in a certain way, and it will come to a terminal velocity in the end.
So vibration will be happen like this and this way. So for example, let's say this is the front view of the rod, but if it vibrates this way, but the washer is touching the other way, then there will be smaller normal force lead to the smaller friction force. However, as a vibration happening this way, and then the washer is contacting this way, then it will add up to the normal force, making the frictional force higher. So since it's based on the conditions, so we cannot really tell that whether it will make the terminal velocity higher or smaller. Because as reporter mentioned, the friction force is the main contribution to the determining the terminal velocity.
I understand.
You agree?
Yes.
So is there any other question from Julie? Please.
Another one. Have you ever considered more than two contact points? More than one, sorry. Can there be two contact points in the washer?
I think at the beginning in the unstable point, it could be sometimes one when it's rotating this way, but if there's two, but then when it reaches the terminal moments, it will always contact two. That's what I mean.
And in our view, we have observed that there's two contact points between a ring and a rod, but we think that it's the force that the rod gives the ring should support the
So you
spinning
think
motion.
there are two contact points throughout the whole procedure?
No, not just for the stable condition, just for the terminal velocity.
So before the terminal velocity, you think there's only one contact point?
There might be one.
I believe it's oscillating. It could be one or two, based on the angle,
Okay.
because it's unstable at the beginning, as I mentioned. Yeah.
Okay, and in the theoretical part, I think there may be a two contact point, but in the reporter's observation video, there's not obvious. You cannot see the two contact point just one. But if theoretical, it can be two contact points.
So is there any other question
view of you. For in the reporter slide, you said if you change the view of the camera, from the opponent, you said if he would change, if your team changed the view of the camera, what kind of result will be changed? Yes.
Because the camera captures the angle of the volume angle, just like the angle of the six. So we should just consider that. So it will change the angle and it will change the velocity of the slide.
It will change the major velocity.
Yes.
I believe that when I approach this problem, I'll rather get displacement for the two rod and then find the vector. So since we consider the vector, I think we can find the basis vector and then multiply with the transformation matrix to make it into the correct basis and orthogonal basis.
And just assume this is a rod, and if we check the point on this way, and we may observe the linear velocity. So if we change the angle of photograph and the camera, so it will affect the linear velocity. Yes, I think.
Okay, I think it's time. So thanks for all the views. And please prepare for
That's the I learned from reading also.
So let's start from the reporters. The score for reporters is 6, 8, 7, 7, 7. And next is the score for opponent. 9, 9, 10, 8, 9.
Thank you.
Finally is the score for reviewers. 8, 8, 8, 7, and 8. Thank you very much.